to explain about what substances will dissolve in water. So we have a variety of solutes. We remind ourselves that the solid part of a solution is called a solute, and our solvent is water. And water is given the title of being a universal solvent, meaning that it dissolves the most things, but we're wanting to know a little bit more about it. So we have a number of solutes listed here, and we've had class members put a little bit of that solid in with a lot of warm water and shake it to encourage it to dissolve if it's going to. And these are our results. So we found some dissolved, some didn't. We're interested in linking that to bonding. So on the screen I have images of some of those molecules for us to decide what they are. So let's just go through them and confirm we agree with this information about the bonding in those solutes. Silicon dioxide is a network covalent. It's made up of silicon and oxygens in that three-dimensional model. We don't normally use the word polar and non-polar on anything other than a discrete molecule, but it is non-polar anyway, even if we followed the rules, because yes, it has an electronegative element, but not a positive and negative end, so it's definitely non-polar. Sodium chloride, we've got a classic example of group 1 metal with group 7 non-metal, definitely ionic. Now, I'm going to flip to glucose next because sucrose and starch are related to it. So if we look over here, here's a picture of what glucose looks like. We summarise its formula as this, a molecular formula, C6H12O6, but structurally it looks like this, a ring with a lot of OH groups on it. And that should stand out and scream to you that it would be a molecule that's polar because it has lots of OH groups hanging off it, and indeed it is. So down here for glucose, we have it's a polar molecule. If we join two glucose units together, we make sucrose, so it's a disaccharide. And it has the formula of C12H22O11, just an H2O short of that formula times 2, because when they join together, it releases a water molecule. And again, the decision of saying that that's a polar molecule applies because of the OH groups hanging out all over it. So for sucrose, we've got polar molecule. Now that trend stops though, because with starch, where we have thousands, and here we've only represented 4 together, has thousands of glucose units joined together, the size ends up overriding the fact that each of the units is polar. So it just becomes too large and unwieldy. So starch, that polymer of glucose, ends up being non-polar. That leaves us with speaking about paraffin. Here's a representation of paraffin. It's a very long hydrocarbon chain. It's definitely a molecule that's non-polar. Potassium nitrate and copper sulfate are both ionic. I remind you that when we have metals like potassium and copper and we stick them with any of our radicals like nitrate and sulfate, they're all definitely ionic substances held together by electrostatic attraction. And then that just leaves us with iodine, whose structure looks like this. It's a non-polar molecule. Now there's a pithy statement that like dissolves like. We want to test whether our results are demonstrating that. Now by that it means that we're acknowledging that our solvent water is polar, so anything that's polar or has a full charge, ionic, should in fact dissolve in water. So let's just grab a pen and see if our results match that. So we're saying, first off, let's just do the polar substances. Do polar solutes dissolve in this polar solvent water? So I'm seeing sucrose is polar and it dissolves, and that glucose is polar and it dissolves. And the converse of that is that non-polar substances will not dissolve. So this is what we're finding here with paraffin being non-polar. It's not going to dissolve in water. And iodine being non-polar is not dissolving in water. So far, this little pithy statement seems to be fine. Now, like also includes the full charge substances which are ionic. So not just a partial charge separation, but ionic substances. And sodium chloride did dissolve, being ionic. Potassium nitrate dissolved, and so did copper sulfate. Now what does that leave us? This is another one that works. Starch being non-polar did not dissolve in polar water, so it follows our rule. And again, silicon dioxide there's no polarity involved, so and also a very large molecule, so we wouldn't expect it to dissolve. So this works well. Like dissolves like does follow. And we're reminding you that we already have a mechanism for why water does dissolve polar and ionic substances. Here's a representation of sodium chloride. When it's put into water, the ions are separated and then surrounded by water molecules. Now, because the cation sodium ion has a positive charge, as all cations do, we end up with the water molecules surrounding it with the slightly negative oxygen end in, and this anion, example chloride, with a negative charge will be surrounded by water molecules with the slightly positive hydrogen ends in. And here our mechanism for why water dissolves polar substances is up here. So this oval is representing a molecule that has polarity, a slightly positive and negative end. And again, we have a similar thing happening down here, that the negative end is surrounded by water molecules with its slightly positive hydrogen in, and the slightly positive side of our polar molecule has the water molecules surrounding it with the slightly negative oxygen end in. So to finish, the thing we need to remember is like dissolves like, but to be able to make predictions, we do need to be able to decide what the bonding is in the solute. Thank you for listening.